Okay, so we can think of circular motion in terms of the linear speed, that is the tangential speed around the circle. We can also think about it in terms of the angular speed, which is how many radians per second you pass, or the angular motion. We can also think in terms of whole cycles. Um, and so we're going to introduce some new variables that are related to motion about a full cycle at a time. So we tend to think about full cycles when we're dealing with periodic motion, and periodic motion is any motion that just repeats at regular intervals. So if we're in circular motion, that's going to be if we're going at a constant speed in circular motion. But we can have periodic motion that is not circular. Maybe we go back and then forth and then back and forth. That's still periodic, but it's not circular. And whenever we have periodic motion, we can define a period. The variable for period is capital T, and period is just the time it takes for one cycle. Pretty straightforward. Lowercase t is used for a generic time interval, and capital T is specifically period, so don't get them mixed up. And since it's time, the standard SI unit is seconds. What we can also define frequency, and frequency is how frequently you complete cycles. So it's like the number of cycles per unit time. So you could go around the circle 10 times in 5 seconds. That's on average 2 cycles each second. So your frequency would be 2 per second, or 2 cycles per second. And the unit for frequency is actually hertz. A hertz is defined as 1 cycle in 1 second. And so we have periods as the number of seconds in a cycle, and frequency as the number of cycles in a second. We can see that they are reciprocals of each other. If we know the period, we know the frequency. If we know the frequency, we know the period. Period's like a time, and frequency's like a rate that we complete cycles. So let's determine the period, frequency, and angular velocity of the seconds hand on a clock. Okay, well, the seconds hand on a clock goes around once a minute. So the period, let's just do it over. The period is going to be 1 minute, but we want that in SI units, standard SI units, so that's going to be just 60 seconds. What's the frequency? Well, the frequency is just 1 over the period. How did I get that? Well, if period is 1 over frequency, then frequency is 1 over period. They're reciprocals of each other. So it's 1 over 60 seconds. And so we just do 60 to the minus 1 power, or 1 over 60. I get 0.0167. And it's units of, well, it's cycles per second. That's actually units of hertz. We might write that as 16.7 millihertz. So we don't have to deal with those extra zeros at the beginning. 16.7 millihertz. And then angular frequency, or angular velocity, that is, again, that's just angle over time, delta theta over delta t. If we're thinking about a full cycle of that hand, it goes around 2 pi radians, and the time it takes is still 60 seconds. So it's just going to be 2 pi over 60, which is 0.105 radians per second. Yeah, 0.105 radians per second. And so you might be able to see that omega and F are closely related, because each of them tells us about how quickly we go around the circle. In fact, they're proportional to each other just by this factor of 2 pi. We can always convert between them too. Frequency is always related to angular speed. Omega is always equal to 2 pi times frequency. Because if we go around, let's say, one cycle, that's equal to 2 pi radians. So omega is always going to be 2 pi times as many as frequency. If we go around 2 cycles, that'd be 4 pi radians. It's always 2 pi times F. And that equation isn't given in your data booklet, but this equation is. Period is 1 over frequency. and it's also equal to 2 pi over omega. And so there's actually a lot going on in this equation. If we want the relationship between omega and f, we can just solve for omega, and we still get omega equals 2 pi f. But we can also get the relationship between omega and t this way. T equals 2 pi over omega. Period is 2 pi over omega, but also omega is just 2 pi over the period. That should kind of make sense just from the definition of angular frequency. It's angle over time. If we go around a full circle, that's 2 pi radians in 1 period's worth of time. So we can also relate speed to period, and since speed is just distance over time, if we go around a circle once, that's a distance of a circumference, which is 2 pi times the radius. And the time is just the period. So speed is equal to 2 pi r over the period. It's also equal to omega r. So again, we have a bunch of different relationships here. In each of these equations, we can relate our linear or tangential motion to our cycles, which is something like this right here, and our angular motion. And depending on what we want in the problem, we'll use either 2 parts of the equation down here, or maybe 2 parts of the equation up here. So let's look at this little problem. The period of the moon's orbit is 29.3 days. It orbits at a distance of 385,000 kilometers. Find its orbital speed, orbital frequency in hertz, and angular speed. I'm going to erase this. And we're going to write everything in our standard units. So let's convert first our period to seconds. So it's 29.3 days. And we have what? One day is 24 hours. And we have 1 hour is 60 minutes. And 1 minute is 60 seconds. So our units cancel, and we're left with conversion to seconds. 29.3 times 24 times 60 times 60 gives me, what does it gives me? 2.53. 0.53 times 10 to the 6 seconds. So that's my period. Period of 1 full orbit. Orbital frequency in hertz. Well, frequency is just the reciprocal of period. So that's 1 over 2.53 times 10 to the 6 seconds. Take the reciprocal of that. I'm getting a very small number, 3.95 times 10 to the minus 7. And the units for frequency are hertz. Okay, so I've got the frequency. What else? How about the angular speed, or the angular frequency? I haven't got that yet. And I'm going to use this equation up here that we already found to relate angular speed to frequency. Omega is just 2 pi times the frequency. So it's 2 pi times 3.95 times 10 to the minus 7 hertz. 2 pi times 3.95 times 10 to the minus 7 is just 2.48 times 10 to the minus 6. And the units are going to be not hertz anymore, we're omega, so that's going to be radians per second. And it's a bigger number than our frequency because we go through more radians in the same amount of time than we do cycles. And then last of all, let's find our orbital speed. Well, orbital speed, we know omega, we can just use v equals omega r. You know, we could also use distance over time. We could use 2 pi r over the period. That'd be totally fine too. But I already have omega, so let's just use omega r. So that's going to be 2.48 times 10 to the minus 6 radians per second times the radius, which is 385,000 times 10 to the 3, writing it in standard units, so I have to convert to meters by multiplying by 10 to the 3 meters, and we get we get 955, really 956 meters each second. So that's about 1 kilometer, actually let's just write it as kilometers per second, 0.956 kilometers each second. It's going pretty darn quickly. Even though the angular speed is very, very small, the radius is large enough that the linear speed can be quite large. So that's that. These are really all of our big ideas kind of stuck together. We have 3 different ways of thinking about circular motion. We have the linear or tangential motion, the angular motion, and the cycles, number of cycles. Angular is radians, cycles is just cycles. We have a way of thinking about the rate that we pass through things, and they're all kind of related. Tangential speed is distance over time. Angular speed is angle over time, and frequency is cycles over time. And then we have relationships between our different variables. To convert from an angular version of a variable to a tangential version, we just multiply by r. And also we can convert to our cycle version by multiplying or dividing by 2 pi or just using these equations. That's all. Bye.